You're listening to The Local Maximum, episode 266.
Time to expand your perspective. Welcome to The Local Maximum. Now, here's your host, Max Sklar.
Welcome, everyone. Welcome. You've reached another Local Maximum, celebrating 5 years of Local Maximums for you this year, actually. That back on February 6th, so 2 weeks ago, episode 264 was the 5-year anniversary of the Local Maximum. Doesn't that go fast? If you've been with us for a while, please consider helping me reach my goal of 50 supporting listeners on maximum.locals.com. I know that there are 50 doesn't sound like that high of a number, but I know a lot of people just listen for free, which is fine. But hopefully I'm trying to get a few people to support us on Locals and get a really great community going there. 50 for 5 years, maybe that makes sense. Not only will you support the show, which you love, for only $4 a month, but you get access to our community where we'll have further discussions and commentary, way better than the discourse that you have on Reddit, I can assure you. Basically, this is just a direct line to me and Aaron, so you could ask us anything. More conveniently, a single month counts. So please sign up with Winter 23. You get one free month, and then just do another free month. And if you don't like it, it still counts towards my 50. So that it's a good one to do. So please help me out there. It's so easy. Last week, we talked about the multi-armed bandit. I thought that was going to go over a lot of people's heads. Maybe it did, but I actually got a lot of emails from people and a lot of messages about the multi-armed bandit episode. People really liked it. People thought it was interesting. People got something out of it. So maybe I'll do more of those kind of mathematics, read paper type of episode. I don't want to turn this show into kind of a PhD seminar or something like that. But I do want to try to discuss ideas and try to figure out, well, what does that mean for technologists? What does it mean for the average person? So I think that helps quite a bit. All right. Today we are going to talk more about technology. We're going to bring you more AI content today, and specifically, we're going to talk about natural language processing, but going further than that, we're going to talk about strategies for thinking about simplicity, complexity, and prioritization, because my guest today, in addition to being a software engineer and a data scientist, is also a seasoned author and a speaker. I just go on his website. He has tons of examples of talks, all with slides. It's all really like interesting and engaging, and kind of gives you food for thought. So it's worth going to his website at I should probably do it at the end, or should I do it at the beginning? But maybe I will just do it at the beginning. It's joelgrus.com, JOELGRUS.com. I'll also give it at the end. I first found him recently at the online conference NormConf with the talk, "What's the simplest thing that might possibly work? And why didn't you try that first?" Joel Grus, you've reached the Local Maximum. Welcome to the show.
Thanks for having me.
I appreciate you having on, and I know you've done some podcasting yourself at one point. So
we're going to bring it back at some point. We keep talking about it.
Really?
Oh yeah.
Okay. Well, what was your podcast called?
It's called Adversarial Learning. It's me and Andrew Musselman.
Okay. So if you want to, when you do bring it back, definitely let us know. Announce it. You could come on this show and announce it, and or I could forward it to my audience. So that's exciting. I'll look into it.
It wasn't deliberately. It wasn't a deliberate hiatus. It was more we just got busy and then stopped recording episodes.
I know that's what happens. It's really, people don't realize doing a podcast episode takes out a lot more than you expect. Like right now we're recording a half hour. And it's like, okay, that's just a little bit of time in my calendar. But then now I realize I have to have wind down time and then rev up time. There's like a whole hour before and after that I need to always block off. But anyway, I first heard of you actually recently at NormConf, which, by the way, I really enjoyed that conference. So how did you hear about that, and how did you come up with your talk? Which that was the only one, that was the main one that caught my eye because the title was "What's the simplest thing you can do, and why didn't you do that?"
So I'm friends with a bunch of the NormConf organizers. Honestly, it was a conference that ran largely on cronyism. And so, I know the organizers, and they asked a lot of their friends to come and speak. It so happens that they knew a lot of people who are prominent in the data science community, one way or another. And so, as soon as they announced it, I said, "Oh, I'll speak there." It's always fun to have an excuse to speak. As for why I chose that topic, a couple things happened. One is that I'm someone who really has always recently embraced the idea of simplicity. And I like simple solutions to things. I like clean code that's not too complicated. I like, trying simple things before complicated things. And so, I used to run data science / machine learning / engineering teams. And when people would bring me something complicated, I'd say, "Did you try something simple first?" And if they said no, I'd say, "Why not?" And after a while, they would anticipate that and then just start trying more simple things. And so that mindset was sort of half of why I started thinking about that talk. The other half was sort of an opposite experience, which is that I started talking to a lot of people who are working on natural language processing problems or text classification problems, and they would tell me, "Oh, I'm trying a naive Bayes classifier," or "I'm going to do word to vec vectors and then something else." Things that in some ways are really simple approaches to the problem, right? If naive Bayes is maybe the first thing you teach someone about how to do text classification, and you can implement it yourself in an afternoon. But at the same time, my reaction was, naive Bayes is so bad compared to using BERT or something and fine tuning it. Like, why would you even waste your time when you're going to get much better results the other way? And so that caused kind of a tension inside of me that, usually I say, try the simplest possible thing first, but here's this other situation where someone did ostensibly a simple thing, and I'm like, why did you waste your time doing that? And so some of the talk was about trying to sort of square those two instincts within myself.
Yeah, so I've been through that with text classification, so I want to get into that in a little bit. But it sounds like, from the talk, I was thinking about it, like it's one thing to say I'm going to embrace simplicity, but in reality, when you do it, it's not so simple. Like there's some deception when it comes to what is simple and what is complex. So I don't know if there's a way. You just spoke about like that contradiction with which is like naive Bayes versus BERT. Like what's at the heart of the tension there? Is that something that comes up in other areas as well?
Yeah, so there's a couple of things there. One is that the naive Bayes is a model with not a large number of parameters, and it's simple to implement. It's simple to train. At the same time, if you talk about BERT, it's a very complex transformer model with millions or probably hundreds of millions of parameters. And so if you compare, here's a model with 1,000 parameters, and here's a model with hundreds of millions of parameters, then intuitively, the one with hundreds of millions of parameters is a lot more complicated, and the one with 1,000 parameters is a lot more simple. And so I think you have a lot of situations like that. At the same time, I use this example in my talk. If you read the BERT paper and said, "I want to apply that to my problem," you were signing up for writing thousands of lines of code to get this thing implemented. And over time, Hugging Face came out with a transformers library and started a hub of all these pre-trained models. And now today you could fine tune a BERT model using 5 to 10 lines of code, probably not any more code than it would take you to train the naive Bayes classifier model. So from a kind of building, tooling, and scaffolding perspective, suddenly you have this very complex model in some sense, which is just as simple to use and get much better results as the model that's simpler in some, abstract sense. And then on top of that, one nice thing, and this is a little bit more to do with text classification or NLP than other things, is that in all these BERT models, you shove your text in as is, right? Because it understands is maybe the wrong word, but it understands that the word walk and the word walking are related and sort of takes that into account automatically. Whereas if you're using a naive-based classifier, you might have to do stemming, you might have to remove stop words. You have to make all these different modeling choices, which are in some ways arbitrary and in some ways are like adding all this extra complexity to the model, because suddenly it's not just I took a pre-trained thing and shoved my text through it. It's I took, a simple thing, but then I started making a large number of decisions about how I want to feed my thing through it.
Right. So I've been through this exactly with Foursquare. I, built out the natural language processing pipeline, and this is all from like 2012 to 2015. And so there was no BERT. But what I ended up doing was, for one of the main applications, it was sentiment analysis, and we had a lot of likes and dislikes. So we kind of were able to put together a large training set. And so started with naive Bayes after some language detection and tokenization and stemming, then moved on to logistic regression, which beat naive Bayes by a lot. And we also did it on like a 4-gram model. So we had all sorts of different phrases in there. The model was really, really cool, but I get what you mean about having to make all of these decisions within that. Like we tried tons of different things. Like, well, would it work to like? I remember one project that really was a waste of time. I was like, well, maybe it doesn't make sense in to do a 4-gram if they like, if the 4 words in sequence span 2 sentences. So, or skip over a comma because they're in 2 different phrases. So let's just like remove those from the features of a given piece of text that we're trying to classify. And so I did all this work, and it was like the end model was worse. It didn't do anything. So,
in some ways, it's similar to the ever-present desire to figure out how to use neural networks on tabular data instead of like XGBoost or something. Because with XGBoost, you have to do all this feature engineering, and there's so many things. Okay, I'll bucket it, and then I'll look at this, and I'll cut it off here. Whereas in theory, if you just throw it into a deep learning model, then maybe the feature engineering you get it for quote unquote free. But I think people have had less success there.
So it sounds like when looking at trying to analyze the complexity of a project, we have to have like a much broader view than it's not just the complexity of the model. It's the complexity of the code. It's the complexity of the team. It's how the abstractions are laid out. There's a lot more to it than just, now it sounds like my analysis of complexity is getting a little too complex.
Right. But yeah, like I think the way I put it was as our tools get better and as our abstractions get better, things that previously were very complex to do and understand and implement become much simpler, right? And so simple and complex are not decisions that can be made in some kind of abstract vacuum, but they're really a function of, what is the tooling we have? What are the resources we have? And so on.
So how do you know if something's ready for prime time? Because there would have been a time with BERT, for example, in like 2018. I don't know when this was, when like it would have been like, okay, this is not ready for us yet. And so how do you, do you kind of have to keep your pulse on the latest research and try to figure it out? And, it seems like you might have one impression and then that knowledge might get old after a few years.
Yeah. So most knowledge gets old after a few years, but I think it depends, right? Like some problems, need state of the art, and some problems every percentage point of accuracy or F1 or whatever is worth millions of dollars if you're doing something at Amazon scale or whatever. And then at the same time, at the other end of the spectrum, maybe it's the case that your Foursquare sentiment analysis model, that if you improve it by 5%, it's not that like it affects people at the margin, but it's not going to like drive that much change. And so I think those are some of the calculations that need to go into it, right? Like, okay, I'm potentially going to get an incremental improvement by staying on top of the state of the art. How much is that incremental improvement worth to me? And that's a function of my problem and my business and so on and so forth. And so I think there are some places where, it would be worthwhile, and they probably have enough people dedicated to it to say, BERT was published, let's try it on our data tomorrow, even though we're going to have to, write a lot of ugly code and debug a lot of stuff and figure out how to get it to work and so on and so forth. And then there's also places where, you say that looks interesting, and once the tooling around it is sufficient that, my data scientists can work with it, we'll give it a try. But that doesn't need to be this month or next month.
Yeah. Yeah. So I think I enjoy these like kind of philosophical discussions about it, because I feel like this helps people, even who are not in data science, even who are not in machine learning, just people who work on really anything. This applies to who are listening today. So let me, I haven't looked at the Foursquare NLP pipeline since maybe 2018, maybe 2019. So help me update my skills. Let's talk about what this is, BERT and transformers. Like what is it doing that either a logistic regression n-gram model or even a neural net isn't doing?
So, okay, I'll do a little bit of a history lesson here.
Yeah.
So, with naive Bayes or like an n-gram model, you're basically saying, I'm going to chop this thing into words and then, basically treat it as a bag of words in some sense, right? So I take a document and I don't care that much about word order modulo what I capture through the n-grams. And I'm just going to count how many times the occurs, how many times bad occurs, and so on. And, now I have a vector of counts, and I'm going to use some method to say, I'm going to turn that vector into, a probability of positive sentiment or negative sentiment, right? And so logistic regression is sort of the natural thing to do there. But the problem is that there's a couple problems. One, you've thrown away word order, and word order is very important, right? Like if I have, negations or whatever, and, I say, this is not terrible. Well, if I don't know to associate the not with the terrible, then you just say terrible. That's a huge negative word. So it's,
that's why the model that we had, where we looked at all phrases of length 1 through 4, actually fixed that problem. I mean, I guess you could have had something of length 5 or some complex thing but it really solved all the problems with that.
Right. So so that will help with the shorter range dependencies. But then when you have like longer range things,
right.
The second problem has to do with like stemming and similar words, right? So like I said, walk and walking, if you're just embedding things as like a vector of, here are the words that are in there, then a 1 in the walk place and the 1 in the walking place have nothing to do with each other than what you sort of train through your objective function, right? But there's no way to bake into there the knowledge that those are sort of the same word and are related and things like that. And so one step from there was then, what you could call the word vector era. So like word to vec, glove vec, where for each word you get, instead of like let's say a 1 hot embedding, where like if it's the word walk, you get a 1 in position 134, which is the walk position. You get some sort of dense embedding in some 500 dimensional space or whatever, and you do it in a way that embedding somehow captures the meaning of the word, so that walk and walking get embeddings that are similar in some sense, right? And so then we've taken a step towards this problem of how do we represent these words in a way that captures their semantics a little bit. And then, so the next step would be, instead of doing this 1 hot encoding or whatever with the n-grams, we could do, do the word vectors, take the average, and then train logistic regression on top of that. But then we still are not taking like word order into account. So then, you can introduce this concept of recurrent neural networks, so like LSTMs and so on and so forth. And what you do is, instead of just averaging all your word vectors together, you sort of feed them into this stateful neural network where, as you feed like one word vector in at a time, it builds up a state that depends on the previous things you've fed in, and sort of puts the word vectors in context, so that, if you have the same word but it's in a different sentence, something sort of slightly different will happen to it. And then you get some state that captures either, a sequence of contextual word vectors, or maybe just a vector representing the whole sentence, and you can classify those. And that was kind of, let's say, the state of the art pre-BERT, sort of. That was kind of what a lot of people were doing pre-BERT. And so BERT did here's what Bert did. Bert said, rather than using these recurrent neural networks, which are sort of a pain because you have to do them one step at a time, right? If I have a sentence with 200 tokens in it, I feed in the first token, update the state, feed in the second token. And so it's a sequential process that, takes 200 tokens. Is they said, instead of doing that, we're going to use, there's this concept of attention that's used within, neural networks, which is basically when I have a position of my input, like what other positions is it related to? And so they replaced the recurrence in the neural network with this idea of self-attention, which is instead of like looking at the things before me, I'm just going to look across all the other positions in the sentence. And the nice thing about that is that I can do that in parallel, right? So each position looks across all the other positions in parallel. So now if I have like 200 spots in my sentence, I can, and I have enough GPUs, I can just do each of those self-attentions in parallel, right? And so that allows me to train much faster, which means I can train much bigger models.
Okay, but and maybe this is I don't know if this is a question that makes sense, and maybe it's where I'm deficient in my my mental model of these transformer models. But if you have a sentence, let's say it's like 20 words. If I'm trying to run through word 5, I also have to pass through words 1 through 4, and then I have to pass through 6 through 20. But it seems like the model's going to have to run a little bit differently depending on what position your word is in, because it has more to look back at and more to look forward to. Whereas in the recurrent neural network, you're just kind of, it's obvious how to pass it in one at a time. In other words, how does it take into account that your history, the word that you're giving it into the network can have a variable number of words before it and after it?
Right. So that's a fair point. But basically what it's doing is it's doing a matrix multiplication that takes each word and then multiplies it by a matrix and then multiplies it by sort of the matrix of all the words, right? And so it's basically the same sort of computation. And the dimensions are set up in such a way that you're doing a matrix multiplication and then you have some length and you get that same length out, right?
Okay. So it sounds like there's sort of a context up to that point, and then there's a context after that point, and those are like matrices.
Well,
am I thinking about this right or no?
Not exactly, because
okay.
Within the transformer model, it's not really making that distinction between before and after like that, the way you're describing it. There are, there were a few pre-burnt models that were basically trying to generate contextual embeddings that were looking at that, and they'd say, I'm going to run one recurrent neural network in the forward direction and one in the backward direction and build up the state from both sides and so on and so forth. But here we're just saying, I have a word, I also have a sentence worth of words, and I'm going to use those two things to generate, some context.
Okay, got it. What have you used this personally? What are some of your what are some of your best use cases when it comes to text classification that you've seen?
So I've done it a lot for so I've done it in a couple ways. One, let's say categorization. So I have a bunch of texts that may fit into like a bunch of different categories, right? So I run a call center and I have all these call transcripts and I know that, this person called because their widget arrived broken and they're upset about it. And this person called because they didn't understand how to read the instructions. And this person called because they're angry because the battery was not included and they thought batteries going to be included. And so if I have a set of categories that, I've decided is how I want to think about, my customers and their problems, then, and I have some labeled data, I can train a BERT model to pick those out quite nicely. And the other thing that maybe I didn't mention that I should was that, for the either logistic regression or even the RNN models that we're talking about, you're basically starting with random weights and trying to learn what's going on. And so you need a lot of data to learn that. With these transformer models, what you're doing is it turns out that BERT is pre-trained on a large corpus of data, right? Like billions of documents. And so what that means is that a lot of quote unquote understanding of language is baked into that from the beginning, which means that for a lot of applications, you can fine tune it using a very small data set and get good results, right? So, rather than having to have, tens of thousands of labeled data points, you could get away with like a couple hundred maybe, and just fine tune the model, which again already starts off knowing all this stuff about how language is structured and
that's
get good results.
Yeah. I mean, that's huge. I mean, it's not just the cost savings, but it's literally like, it sounds like you could almost get away with doing labeling in-house. 100 labels, 200 labels, like a person could do. Okay. Like maybe, get an intern if you need to do like 1,000 or so, but like, it's not,
I'm probably exaggerating a little bit, but not like, not much.
Right. Well, yeah, but it's not, no, like, we were using hundreds of thousands, to get logistic regression. I don't know if it probably could have worked with less. I mean, I guess we could see that because it was like we were running one for every single language, which was like, maybe the top 5 to 10 languages kind of worked. And so maybe the 10th most popular language had like 40,000, 50,000 examples. But yeah, how does BERT, by the way, do with different languages? Does it have a different model for every language, or does it kind of is it kind of a universal understanding type of a thing?
I know people have trained different ones for different languages, and they tend to give them cutesy names. Like I think there's one called like Camembert, which is French, and so on and so forth. I don't actually know off the top of my head how the original BERT does on multilingual stuff. I know some of these big transformer models, people do train them to be multilingual. I'm not sure. I don't actually know if the BERT is like that or not.
It's always an interesting problem because it's never quite as cut and dry as you want it to be. It's never like, oh, these different languages are all, different walled gardens where each user is going to speak one language and each piece of text is going to be one language. And it's not even the case that each piece of text has the same character set from like one sentence to another. So oftentimes we run into these problems, at least I did. And I'm sure that's probably
right. I mean, on some level, all these models are doing is learning, associations between words or tokens, right?
Right.
So like BERT is trained off of this objective of masked language modeling. So they'll give it a sentence and then like blank out a few of the words randomly, and then the model has to learn to predict what is the missing word, right?
Right.
And so, if in theory, if you feed it like a lot of English sentences, but also a lot of Spanish sentences, then it will learn, both of them, right? Because when it sees surrounding Spanish words, then it'll predict the missing Spanish word and so on and so forth. Now, in practice, I don't know if that's, the best thing to do, or if having different models is the best thing to do.
Yeah, I'm pretty sure the logistic regression model would do worse if we kind of just threw all the languages in there. Because even though, well, first of all, sometimes the same literal characters have different meanings across different languages. And then secondly, it would, I don't know. Well, first of all, it would also like, it would also be like a lot more space because we'd have to, at least for the logistic regression model, we'd have to, I don't know. Maybe it could work. I didn't try it. It just doesn't seem like it would work very well.
Well, the thing that's hard to wrap your mind around, I think, is that the model capacity in these transformer models is huge, right? So your logistic regression model, even if you go up to 4 grams, you're still, it's still like thousands of parameters, right? Like thousands of features and weights for thousands of features.
Oh, it could be way more. I mean, we ended up throwing out everything that wasn't used at least like 5 times in the corpus, and still that was enormous.
And so, in the BERT model, again, you're talking about like literally hundreds of millions of parameters, right? And so within hundreds of millions of parameters, there's a lot of space to learn patterns.
Right.
And so there's room to learn multiple languages. And for instance, if you go to like ChatGPT, for instance, which is a bigger model than BERT, but if you go to ChatGPT and you start like talking to it in a different language, it will answer in a different language.
Yeah. Oh, I should try that. That sounds pretty cool. So this is kind of exciting. Like I am looking forward to hopefully, if I have an NLP project in the future, working with one of these models. It sounds really neat. What do you think are some common mistakes people make when they're doing NLP and text classification, or things that could go wrong?
So one thing that can go wrong is if your data is labeled poorly. And so a lot of times what I've seen is in multi-class classification, the classes are maybe not distinct enough, right? So, if you're trying to determine what is this, complaint about, to go back to my earlier, example, and one was batteries not included, and one was, I didn't receive it on time, things like that. Like, if your categories are not distinct enough, then even like a perfect labeler will still like get it wrong, right? Because they'll say, "Oh, I guess it's this or that," and so I think that's one problem that I run into multiple times in a lot of contexts. I think.
Yeah.
Oh, go ahead.
Oh, I was just saying, I agree. I was going to give some personal examples, but if you had one more.
No, go ahead.
Yeah. Well, no, I mean, I think, so there were things like some of the classifications that we did include sentiment analysis, which did have some wiggle room. Like there were some mixed reviews, and then there were some kind of statements that were not reviews at all. And so we had really 4 different categorizations there. And then in addition, it was like our data set had 3 classifications, which was just like, people saying like, dislike, or the middle one, which is really ordinal data, but we treated it as categorical data. But then there was like spamminess and I think the big one was quality. Like, are these like Foursquare reviews, Foursquare tips that we want to show people? Or is this just a monkey banging on the keyboard? Now, sometimes it's obvious. It's just a monkey banging right here. But in other times it's like, I don't really know what's high quality. Like we disagree about that. And so it was very, very subjective.
And yeah, that's really one of the biggest problems I see in text classification, which is that if you can't get like smart humans to agree on what the right label should be, then you're going to have a real hard time getting a computer to be able to come up with them, right?
Yeah. Yeah. And I've also run into this problem, and I don't know if it was a problem, but so much of we built a model. Maybe it was the sentiment analysis model. And then I was like, okay, let's look at like the top 100 that it labeled as positive that we labeled as negative. So I looked at the top 100, and most of them were like, well, we mislabeled it. So in other words, the model was doing better than we were. And so I'm like, I asked my manager, I'm like, should I change these in our set? I don't know. It sounds awfully, arbitrary, but we probably should. And so it was, I kind of ran into that. I don't know if that was necessarily a problem. It was just an interesting kind of situation.
Yeah. I mean, my experience is that, look, if you have labeling errors that are sort of random, right, then, and you have enough data, the model is going to learn around them, right? But if you have labeling errors that are like systematic, then the model is going to learn those systematic errors as well.
Yeah. Yeah. But when you look at like the top lists of disagreements, then it looks like you have much more, it looks like you have so many more labeling errors than you really do, or at least in terms of percentage, because you're literally focusing in on them.
Yeah, because you're finding like the worst mistakes, right? Like
right.
This was one that was like obvious to the computer, and so we got it wrong. If you'll get the other end, then you'd find the opposite, right?
Yeah, exactly. Although interestingly, there was a model that I did once that was not text classification, but it was trying to predict users' age and gender based on where they went, because Foursquare's location-based system. So it was like locations you go and gender. And it turned out that the ones that got wrong, it wasn't mislabeled. It was usually just, people who were married and were hanging out with their, we're just always with their wife or husband or their spouse, opposite gender. So it made that kind of error, but that was because of the nature of the model more than it wasn't like, it wasn't like, you like to do things that the opposite gender does. It wasn't like that at all, which was kind of interesting.
That's how you know you're doing it a long time ago, because today you'd get in trouble if you tried to predict people's gender.
Oh yeah, well, it was it was 2017, so it was getting there. I think I had to do a few caveats, like, hey, this is just a model, it's for marketing. But then I was totally fine. I don't know. Today, I don't know if I would even attempt that. But that happened. So, all right. I want to, before we head out, I want to hear a little bit about the book you wrote, Data Science from Scratch. We don't have time to go through all of it, but just like, what was it like to write that? Why did you decide to write it? Tell me a little bit about that.
Boy, so I wrote that book in 2014, so it's been a long time now.
Okay.
No, I
long
talk
ago.
about it. I'm just like, it requires me to delve into my like long ago.
Yeah.
I mean, the second edition came out in 2019, but so a couple of things. One, it's a very like self-aggrandizing story. Like I wanted to, data science was becoming like a big thing, and all these like, famous data scientists were like coming up and getting quoted. And I was like, oh, I want to be like a famous data scientist. So like, oh, how can I do that when I'm just like some dude working in a startup? It's like, I know I'll write a book. And then, I studied math in school, and I went to math grad school for a bit. And so I have this very mathematical like pedagogy in my head as a way to learn things. And I like learning things kind of from first principles. And so I thought, actually I pitched a book that was much bigger than the book I ended up writing, which like part one was, here's all these models and here's how they work from first principles. And then part two is, here's the libraries you'd use if you wanted to use them actually in real life. And O'Reilly said, that's 2 books, and we're not giving you a 2-book contract because we've never heard of you. And so I said, okay, fine, I'll write the first part, someone else write the second part. So it's basically the premise of the book is we're going to understand how data science tools and techniques work by building them ourselves in like base Python, right? So, okay, logistic regression, we are going to like code up logistic regression from scratch and then try it on some problems. And like naive Bayes, we're going to code it up from scratch and then try it on some problems. And then, the second edition, I added some more stuff, and it goes all the way through like neural networks and RNNs and things like that that are in there. So, that was kind of that's the way I like thinking about it, and so that's how I read the book.
One of the things I've learned. So I just submitted like a paper to archive. It's like 30 pages on probability, and one of the hardest things that I ran into that I wasn't expecting was like how to order all the things that you want to talk about so that once you talk about something, you've already established all the necessary background and definition before that. And I felt like I spent so much time kind of reordering things and then reading through it and being like, oh, wait, this doesn't make sense because, we haven't introduced this next thing yet. And so did you run into that problem at all? And I don't know, I just asked because it's like, it's on my mind. And how did you guys deal with it?
I wouldn't say I ran into that problem, but it was definitely something I had to take into account when I was kind of plotting out the book. And so, the way I read the book is I basically like made a list of chapters, and then I did that kind of topological sort, like this chapter needs to come before this other chapter because I want to use this. And I took the original Andrew Ng ML class, which was sort of like the first MOOC,
right?
And that class used kind of gradient descent as an organizing principle, if you will. So like, let's learn about gradient descent, and now let's use it to solve a bunch of problems. And that was pretty influential on my way of thinking. And so my book, I kind of did something similar, which is that, we go through gradient descent in great detail, and now I can use it to do linear regression and logistic regression and so on and so on. So, it took a little bit of work, but in general, things were, I sort of designed it from the beginning so that I had things in the right order. And there were a few things where it's like, oh, I guess I'm going to have to move this one topic into an earlier chapter than I would prefer to move it into. But for the most part, it wasn't too bad.
Yeah, it sounds like a little bit of topological sort planning goes a long way.
Yep.
Although I found sometimes, you end up having to introduce things that you didn't even realize when you were writing about something.
And so, actually, that was one of the, not exactly that, but like, one of the most humbling things about writing a book is that you discover that most of the things you thought you understood, you don't understand. So like when it came time to write the section on like inference and hypothesis testing, and I started like writing out how does hypothesis testing work, and I quickly discovered that like I did not understand it well enough I thought I understood it, but I did not understand it well enough to write about it. So I had to like go off and like study and like actually learn it so that I could write about it sensibly.
Yeah, yeah. I mean, that's one of the benefits of writing too, because then you really understand something. It was like, well, if you can, it's also like if you can explain it back, then you understand it well enough. And there have definitely been things like, I'm really excited about X, and then someone's like, explain it to me, and I'm like, I guess I don't understand it well enough to.
I know. I'm worried that my earlier explanations of Transformers were not quite right enough, and someone's going to get angry at me. But well, I apologize if that's.
Don't worry about it. Don't worry about it. This podcast is more of like a discussion with people in tech. This is kind of like this podcast is often like what's on your mind pre-book. This is not, hey, this is like our final course on BERT. This is like, hey, what's interesting to us now and what's on our mind about it to kind of get people excited.
Never underestimate the propensity of people to like listen to things and say, I can't believe you said that it works this way because it actually works this other way, and like you can ask me about it.
I will let you know if I get an email about it. Right. So but I'm pretty sure you're good. Joel, thanks for coming on the show. Do you have any last thoughts on what we talked about today? And tell the audience where we can find out more about you and where they can contact you and all that.
So I can be found on Twitter. It's my name at Joel Grus, JOELGRUS. I'm like one of the Twitter holdouts. As everyone else moves to Mastodon, I'm going to keep staying on Twitter because I like Twitter. And I haven't found a Mastodon server whose terms of service I can live with. I also have a website, which I very rarely update, but that's joelgrus.com. Again, my name, JOELGRUS. And all my contact information is there, but really Twitter's probably the best way to get in touch with me.
All right. Awesome. Joel, thanks for coming on the show.
Thank you.
All right. That was a lot of fun. I've been busy conducting a lot of interviews, and we're really going to branch out over the next month, which is exciting. Next on deck is another Bayesian thinking interview, which for us, I guess, isn't branching out as much as it's going deep, but some of the further ones down are going to be branching out. We've got an interview on hardware, which I think you'll find fascinating. We're going to try to intersperse these interviews with the solo shows and the discussions with Aaron on current events. And, those solo shows and co-hosted shows are also going to have the probability distribution of the week segments. Today's episode, once again, is localmaxradio.com/266, where you can get all the links, including a link to joelgrus.com to get his website. Have a great week, everyone. That's the show. To support the Local Maximum, sign up for exclusive content and our online community at maximum.locals.com. The Local Maximum is available wherever podcasts are found. If you want to keep up, remember to subscribe on your podcast app. Also, check out the website with show notes and additional materials at localmaxradio.com. If you want to contact me, the host, send an email to localmaxradio@gmail.com. Have a great week.
Feel the power.